Hello everyone, I'm Zhang from Lambda Group, Nanjing University. I'm very glad to be here to introduce our work, a simple online algorithm for competing with dynamic comparators. In this work, we consider the full information and learning and design a simple and computationally efficient algorithm which can exploit the adaptivity in the non-stationary environments. This is the outline of my talk today. I will first introduce some background knowledge, mainly including the adaptivity and the non-stationarity in full information and learning, and the fully adaptive bound. Then I will present our approach and some empirical studies. In this paper, we consider the framework of online convex optimization. In the OCO framework, there is a learner making a decision from a convex set in each iteration. Then a convex function is revealed by the environment, as the learner suffers an instantaneous loss. The learner's goal is to suffer as less loss as possible. A classical measure of an online game is a static regret, which compares learner's decision with a single best decision in the hindsight. Linkage shows that the static regret can be bounded in the order of square root t by online gradient descent algorithm. This rate is known to be minimax optimal of convex functions. Although the minimax optimality is achievable, there are two directions to improve the static regret guarantee. The first is to design more adaptive algorithm, which can exploit blind environments while safeguard the worst-case guarantee. Examples are the variance bound and the gradient variation bound. As we can see, in this bound, the dependency on t is replaced by adaptive terms, which can be much smaller than t in benign environments, while is at most in the order of t in the worst case. Thus, these bounds are strictly better than the square root t guarantee. Later, in the similar work of Rakan and Zhi-Hua, authors propose a general framework to unify the previous studies. The regret is bounded with dt. The differences between the gradient and the predictable sequence is mt. With the proper setting of mt, the last bound can imply the previous bounds. Thus, in this paper, we only consider this kind of adaptivity. Another direction to improve the static regret is to compete with dynamic comparators. The dynamic regret is always used as a measure, which compares learner's decision with the minimizer of the online function at each iteration. It is well known that a sublinear dynamic regret bound is impossible unless we impose certain restrictions on the environments. Actually, there are two kinds of regularities in literature. The first is the Parsonage CT, measuring the fluctuation of the comparators. When the value of CT is known in advance, online gradient descent can achieve the dynamic regret in the order of square root t times 1 plus CT. Another regularity is the temporal variability, Vt, measuring the variation of function values. When the value of Vt is known in advance, again, the dynamic regret can be bounded in this order, which is known to be minimax optimal for convex functions. As we can see, there are two directions for improving the static regret. A natural question arising here is that, can we exploit the adaptivity in the non-stationary environments? Meanwhile, as there are two different regularities, can we track the minimum of them to obtain a tighter bound? This question has been studied by the similar work of Jadbabaie et al., where authors propose a fully adaptive bound as shown in this table. The fully adaptive bound enjoys two merits. First, it tracks the minimum of the two regularities. Meanwhile, it can exploit the adaptivity by replacing the dependency on t with dt, which can be much smaller in benign environments. However, this is not the end of the story. Since the previous work achieves this bound by a carefully designed doubling trick method called LMD. For checking the doubling condition, LMD requires to calculate the instantaneous of Vt, which would incorporate a non-convex program at each iteration, and is time-consuming to solve. In this paper, we design a simple and computationally efficient algorithm, which avoids solving the non-convex program and achieves a fully adaptive bound. Our start point is an optimistic mirror descent, which is a mirror descent with an extra gradient state to exploit the predictable sequences MT. As shown by Rakan and Zhi-Hua, the method ensures a static regret in the order of square root dt. In this paper, we show that the adaptive term can also be incorporated in the non-stationary scenario. The first is the Parsonage bound as follows. As we can see, if we consider the optimal step size, the dynamic regret is bounded in the order of square root 1 plus ct times 1 plus dt, which essentially combines the non-stationarity with adaptivity. However, the value of dt and ct is unknown in advance. Thus, this optimal tuning is feasible. The same problem also holds for the comparability bound. The question here is how to tune the learning rates, even dt, vt, and ct are unknown in advance. Different from the doubling trick method proposed in previous study, we use a master-based framework to search the optimal step size. The idea is to run several base optimistic MDs with multiple step sizes, and then use a master algorithm to update their weights and aggregate their predictions. As for the base algorithm, we show that there must exist an optimistic MD drawing the desired harshness bound or the temporal variability bound. Even better, we can actually track the minimum of the two regularities and achieve tighter bound. As for the master algorithm, to make compatible regret bound, we design a novel master algorithm based on optimistic hedge. Our new algorithm can track the prediction of any base algorithm in the regret of square root 1 plus dt. This is the summary of our algorithm. Combining the master regret and the base regret, we obtain the fully adaptive bound. The main advantage of our algorithm is that we do not involve any non-convex optimization problem, which is more computationally efficient than the doubling trick method. Meanwhile, we can further accelerate the algorithm by running base algorithms with a surrogate loss, which will reduce the gradient querying complexity to 1. Finally, we present some empirical studies. The contenders are optimistic MD with static regularity, the doubling trick method LMD, and our algorithm. Figure A and C validate the effectiveness of our method, as it can achieve comparable performance with LMD in non-stationary environments. Meanwhile, our algorithm can also exploit the adaptivity, as shown in Figure C. Figure B presents the running time. We can see that our algorithm dramatically improves LMD, as our method runs 24 seconds for 6,000 iterations, while LMD requires around 6 hours. In summary, in this paper, we design a computationally efficient algorithm with fully adaptive bound. Our method is based on the master-based framework, and our novel master algorithm is carefully designed to achieve the compatible bounds. Empirical studies also validate the effectiveness and the efficiency of our method. This is all of my talk. Thanks for listening.